I'll start by thanking the organizers for inviting me. I'm going to talk about multilinear maps. This is joint work with Craig and Shai. Okay, so I'll start by talking about what bilinear maps are. I'll tell you a bit about some application. I'll give only very few applications, and in the process will motivate multilinear maps. I'll tell you about our results. Again, there are a lot of applications for multilinear maps that have come up. I'll give two representative applications, biased by what I like. Then I'll give you the definitions for multilinear maps as have been classically envisioned in the literature. And then starting from this notion as envisioned in the literature, I'll step by step give changes that need to be made to get our notion. Then finally I'll get to our construction and say a few words about the security. Okay, so let me start by defining bilinear maps. So bilinear maps are this extremely useful tool in cryptography. They have lots of applications. I've not cited or said anything, but there are a lot of them. And as the name suggests, it allows pairing two things together. So more formally, bilinear groups, cryptographic bilinear groups are these groups G1 and G2, both of prime order P and with generators G1 and G2 respectively. But they come equipped with this bilinear map E, which takes two elements from G1. So from the group G1, it takes two elements and maps it to an element in G2, such that this condition holds. So if you pair G1 to the A with G1 to the B, you get G2 to the A. Okay. So what's going on is the exponents are getting multiplied. Okay. So DDH is a problem, decisional Diffie-Hellman problem, which in general cryptographic groups where you don't have this pairing operation E is considered hard. And the problem states that if I give you G1 to the A and G1 to the B and a challenge value T, your goal is to determine if T looks like G1 to the AB or is random. In usual cryptographic groups which do not come with this map E, it's considered hard. But as you can see, if I give you this, these cryptographic groups have this additional map E along with, then this problem is actually easy. You can just pair together G1 to the A with G1 to the B, and check if it's the same value as G1 to the, pairing of G1 with T. So in this case, you will get the exponents will get multiplied. The T already has AB in the exponent and it gets multiplied with 1, and so you can check. But still, actually, the problem of coming up with the value G1 to the AB still remains hard in these groups. So this kind of a disparity between the decisional and the computational variant allows for a lot of applications. So the instantiations come from Wheeler-Tate pairing over elliptic curves. These assumptions are useful, but in the setting of bilinear maps, we would like to make other computational hardness assumptions, which are believed to be hard as they're conjectured. And one of these ones which is really useful is the bilinear decisional Diffie-Hellman assumption. The assumption states that if I give you G1, G1 to the A, G1 to the B, and G1 to the C, all in G1, it should be hard to distinguish this value G2 to the ABC from random. So remember that it's easy to multiply two things in the exponent for free, but as soon as I put a third thing, it becomes hard. So just bilinear allows for two things easily, but three things are hard. Okay, so now I'm going to give this very simple application. I'll start with the application in groups where you do not have these bilinear maps, and this goes back to the work of Diffie and Hellman. And the idea is simple. We have two parties, Alice and Bob, and they want to non-interactively send one message. So each party gets to send one message at the same time, so they don't get to see what the other party sends. And they should be able to establish a shared secret key at the end of the protocol. So what Alice does is samples a random value A, generates G1 to the A, and sends it to Bob. And similarly, Bob samples a random value B, generates G1 to the B, and sends it to Alice. At this point, both of them can compute G1 to the AB. So Alice knows the value A. It can exponentiate G1 to the B with the value A and get G1 to the AB. And similarly, Bob can use the knowledge of the value B too. But no third party can actually even distinguish this value G1 to the AB from random. Okay? Now, if we had these groups with bilinear map, then we can actually do a bit more. So we can do the same protocol in the setting of three parties. Okay? So what would and this protocol is due to Ju. And the protocol is simple. We now have a third party, Carol. And what it does is analogously samples a random value C and sends G1 to C. Okay? So bilinear maps allow you to multiply two things in the exponent for free. Third value I can exponentiate because I have knowledge of one of the secrets. So what Alice can do is pair together G1 to the B and G1 to the C, and it gets E, G1, comma, G1 to the BC, and it knows A, so it can exponentiate the A. Okay? And by the assumption that I just stated, this three-party decisional bilinear, this assumption, so with some name to it, which I gave, is hard, then we can say that this shared key cannot be distinguished from that. So what if we had more than 3 parties? So this a protocol that I just described can be extended to a setting of multi-parties if you had multilinear maps. And this is due to Bonnet and Silverberg. In their paper, they showed that if you had multilinear maps, you could do this for more than 3 parties. And you could realize a lot of other applications. But they showed that it should be hard to realize multilinear maps, at least from the techniques that we know, which are used to realize bilinear maps. Okay, so now I'm going to tell you a bit about results and applications. So we give constructions of multilinear maps. There are a bunch of caveats. The first being that they're candidates. So what I mean by that is, we cross our fingers and hope that meteors will not come and will not break our scheme. I don't know. So we're hoping that they won't break. We have some cryptanalysis to support it, and that's it. The second is that they're approximate. So what I mean by that is they do not realize the envisioned notion of multilinear maps, but an approximate version. So I'll get to defining what it is. So there are lots of applications that you can get out of multilinear maps. I'm going to give 2 applications. One is witness encryption, and the other is indistinguishability obfuscation. So these, in my eyes, are like the representative applications of what we can reach in terms of cryptography using these tools. So I'll start with witness encryption. So the idea is simple. So think of an encryptor. He has this message M. He has this statement X in the sky. And what he wants to do is that he wants to encrypt this message M corresponding to this statement. The statement X is like any instance of an NP statement. So think of any crossword puzzle that appeared in some newspaper or your SAT formula, and you want to encrypt this message corresponding to this statement. Okay? So the encryptor generates this ciphertext and puts it out there. Any receiver who has a witness for this statement should be able to decrypt it. So he should be able to recover back the message in polynomial time. So note that the encryptor is not aware of any witnesses for this statement. So it's not, and in fact, it doesn't even know whether the crossword puzzle or the SAT formula is satisfiable. It's just encrypting it, and the receiver can decrypt. And the soundness condition is that if the statement is false, if the SAT formula is actually unsatisfiable, then semantic security should hold. What that means is that the receiver shouldn't be able to tell whether I encrypted 0 or I encrypted 1. Okay? So this, if you think about fully homomorphic encryption, it's really cool. What it allows you to do is arbitrary computation on encrypted data. But what you get in the end is encrypted. Okay, so yes. Yes, complicated. Statistically, actually, it's known to be impossible for all of them, unless the polynomial hierarchy collapses. Okay, so getting back, so if we think of FHE allows you to do arbitrary computation on encrypted data, but what you learn in the end is also encrypted. What this allows you to do is the computation is entirely public, so whether X is satisfiable or not for the receiver is completely, but the message is hidden based on that. So it's enforcing the maximum level of, or whatever we can think in terms of access control. Okay. Now I'm going to give you about another notion in distinguishability obfuscation. This notion is stronger than witness encryption in the sense that it not only allows you to do this access control, but it mixes it with FHE. So what you're learning is arbitrary computation of encrypted data and not just encrypted answers. Okay. So we have this obfuscator, and this he holds a circuit C, and he obfuscates this circuit and gives to Alice. So what Alice can do now is she can run this obfuscated circuit on any inputs of its choice and learn the output. And the security guarantee is that if she couldn't tell whether this circuit C is C1 or C2, conditioned on the fact that C1 and C2 are functionally equivalent, so they on every input they behave in the same way, and they are of roughly, let's say, the same size. Okay? So this allows you to achieve all these cool notions, and So the strongest notion of obfuscation, as we know, is impossible to realize. But whatever notion of this is like a weakening which we don't know as being impossible, and this is something we can realize. Okay. So let me start by now. Hopefully, I've convinced you that multilinear maps are useful. I'll give you definitions for multilinear maps. I'll start with the classical notion. I'll tell you about our notion. Okay, so just like we had bilinear maps, now I'm going to have these groups G1 to Gn instead of just G1 and G2. All of, let's say, prime order P with generators G1 to Gn respectively. Okay. And instead of requiring just this one bilinear map, I'm going to require a family of maps which allows you to pair elements from any of the two maps and map it to an element in such that the subscripts get added. So think of it as a layered structure. You have G1, G2, G3, and so on up till Gn. And you can pair two elements from G1 and go to G2. You can pair an element from G2 and G1 and go to G3. Or you could map two elements from G2 and G2 itself and go to G4. You can keep doing it as long as you don't hit the ceiling. And the ceiling being the level of multilinearity, that being n in our case. Okay. So we hope that in this setting, at least the discrete log problem is hard. So what I mean by that is that if I give you something in gi to the a, then you shouldn't be able to go back a level down. So get gi to the a minus, gi minus 1 to the a. Okay, so something, yes. In the sense that if you pair two things and then you can pair it with something else, then the things should be the same. Yes. Yes. So for some applications it is important, for some applications it's not necessary. So for some applications you could just pair all the things together and that's all you care about. For some applications, let's say I compute a map and get something and then you give it back to me and I then am supposed to pair it with something else and give it to somebody else. If it's an interactive process where the final group is only reached at the end of the thing, then it would be important, right? Right. So, yeah. So I'm saying that for some applications that might be important, for some it may not be. So for some, it might just be enough if you have just everything at the first level and you can just go directly to the nth level. You don't need any intermediate levels at all. That doesn't affect us in any way. Yeah. Okay, so I'll give our notion, and how I'm going to give it is I'm going to first give like this very simple visualization, like a pictorial visualization for bilinear maps, and then I'll step by step give changes that need to be made to get our notion of bilinear maps. And going from there to the notion of this multilinear maps, which is the approximate multilinear maps for our setting, is going to be easy. Okay. So bilinear maps have this setting ZP, G1, and G2, and ZP has these elements 1 to P, and G1 has these corresponding elements G1 exponentiated with 1 and 2 and so on. And you have G2 where G2 is the pairing of G1 with G1 itself, and you have the value exponentiated. Okay, so there are certain properties in the setting of bilinear maps which we take for granted. Like for example, you can sample uniformly from CP. Okay. Another property is you can check if two values are equal because each element is being represented in just one way. So if I look at G11, there's only one unique representation for this element, so you can check in efficiently by looking at the bit. If I give you the same element twice, you can just compare bit by bit, and then you can say that these two are representations correspond to the same element. Addition is also easy. If you want to add two elements in G corresponding, if you want to add, if you multiply the encodings of two elements in G1, what you're getting is an encoding of the sums of the encoded terms. So here G1 to the 1, and then you multiply with G1 to the 2, the exponents get added, so what you're getting is a sum in the exponent. Okay. When you pair, what you're getting is multiplication. So when you pair G11 with G12, you get G22. So the first approximation for a setting is that we're no longer going to have these elements being single, like each element having a unique representation, but each element is going to be represented by a set. So this element 1 is going to have a bunch of representations. I'm going to call them the set S01. So level 0 encodings of 1. So the subscript is the level of number of the encoding, and the superscript is the term being encoded. And so on for G11, I can have S11. In G1P, I can have S1P, and so on for G. Okay? So for the multilinear setting, we will just have more of these sets. And I'm going to call the union of these sets as S0, which is the set of all level 0 encoding. And similarly, set of all level 1 encoding and set of all level 2 encoding. Okay? Okay, so what I'm doing is think of this ring R, and these sets Si are the if you have n levels, these are the set of all encodings at level I, and each of them can be partitioned into the subsets SIA for each element in the ring. Okay. Okay. So I said that it was in the setting of bilinear maps, or in general in ZP, it's very easy to sample uniformly from ZP. We're going to require an analogous property where we say that it should be easy to sample from the set S0, but the requirement is that if I sample an element from S0, it's going to come from one of these sets. I'm going to require that it be uniform as to which set it comes from. So in particular, if I sample alpha from S0, there's going to be an induced distribution on A. I'm requiring this distribution of A be uniform over ZP. Okay? I'm not requiring that the element be uniform within the set it comes from or from the entire space, just that the set it comes from be uniform. Okay. Next, equality check in the setting of if you have general cryptography groups, it's easy because each element has one unique representation. Now we have to have the same property even when we have sets. So if I give you two entries from this set, they represent the same element. You should be able to in polynomial time tell that they represent the same element. So for every level of the encodings I, if I give you two elements A and B, such that both come from the same SIA, then you should be able to tell. Okay. Okay. So again, recall addition was easy, and then in our setting, we're going to require that if you take any element from S11 and an element from S12, there be a canonical addition operator that on addition of any of these elements, you get an element in S1. And so similarly, you can define subtraction, and can be done at any level for the and multiplication is corresponding to the pairing operation in the setting of bilinear map. So if you paired elements here in G11 and G12, you got G22, and we're going to now require that if you pair any element from S11 with an element in S12, then you get an element in S2. Okay? Yeah. You mean? Yeah. Yes. So in the setting of S11, we are hoping at least discrete log is hard, so it hides the value. So there has to be some canonical addition operator. Yes. Now the final requirement is that we're going to our maps are going to be noisy. What that means is that all the operations of addition, equality, check, everything that I stated are not required to hold for each of these sets completely. I'm going to look at a subset within each of these sets, and all the operations that I just stated are required to work as long as you remain in that set. So it's like the small noise domain. So if you go too large, then things go crazy, and we have no guarantees. So within these sets, we have the small region where all the operations that I just stated are required to hold. If you go beyond this region, then none of the correctness property that I stated are required to hold. Yeah.
Do you know the zero element, for example, if you try
like, this is just the definition. I mean, what representation you might have is a different story. But
I mean, you can add, can you almost subtract?
yes.
Okay, so I can compute it. Right. Can you divide?
Well, I mean, zero itself is a zero, right? I mean, the zero term in our representation is going to correspond to the zero of these sets.
So there is a trivial way.
Yeah. Yeah.
So there is a trivial way to build a
Right.
no.
No.
But it's the
Yeah, it's a property of the particular.
Trivial way of representing one?
No. So I mean, the trivial way of representing one in the first zeroth level, not beyond that. Like one itself is.
So the one in the zero?
Yes.
And do you also know the key characteristic of your ring?
That can be made public. Yes, that's not a problem. Yeah. Yes. Right. So that's something is not required by the. You want that from the scheme, right? That this is the definition that all the correctness is valid only as long as noise is involved. For the scheme, you will then require that, oh, if I perform these operations, then I will guarantee that the noise has not grown and I can still do all these operations. Yes. Yes. Right. Then you're satisfying this trivially, right?
So can slide again?
Yeah. Yes. Okay, so as I said, at least we hope the discrete log problem is hard, which says that if I give you a level j encoding of A, then it should be hard to get a level j minus one encoding of A, and hopefully stronger assumptions can be conjectured to be hard. So for example, it would be nice if we had n multilinear decisional Diffie-Hellman assumption. What that says is that if I have separate encodings, let's say level 1 encodings of 1, A1, and up to an plus 1, then I cannot distinguish a level n encoding. Let's say I give you a challenge, level encoding T, I cannot tell whether it's an encoding of the product A1 to an plus 1 or just something simply random. So what I'm trying to do is that the level of multilinearity is n, but I'm trying to put n plus 1 terms in the exponent. You could easily put n terms there, but this extra 1 term should make your life hard. Okay. Okay, so now I'll give you the construction, and maybe things will become more clear. So yes, just a remark. So our scheme is very much like the n-true-based fully homomorphic encryption, but there's a equality testing thing at the highest level, which allows you to have the. So we're going to work in polynomial rings where fx, as we heard yesterday, is going to be the xn plus 1, where n is a power of 2, so it's a 2nth cyclotomic polynomial. And we're going to use the ring RQ, which is R additionally modded out with Q, and think of Q as being very, very large. Okay, so it's yes. So do we need it to be prime? No, we don't need it to be, but yeah. So let's think of it a prime for now. Yeah. I mean, at least it should have large prime factors because we'll need things to be invertible. But so let's start with it being a prime. Okay. So our public parameters are going to be such that they hide this small parameter g. So what I mean by small g is this an element. If you look at the coefficient representation, the coefficients are small. Okay. And since it's small, it's going to be the same value in RQ and R. Okay. So Q is really, really large, and the elements, the coefficients of G are small. So it doesn't matter whether I look at an RQ or R, it's going to be the same value. Okay? And then I also have the secret parameter Z, which is a random in RQ. So it's going to be, since it's random in RQ, it's going to be large. Okay? So it's a random value, hopefully it'll have coefficients comparable to the size of Q, and it'll be large. Now let's say this G defines a principal prime ideal over R. Yes. Okay. And what I'm going to look at is the scalars corresponding to the ZP in the definition that I just stated are now going to be sets, which will going to correspond to the cosets of R by I. Okay. The quotient ring R by I corresponds to the ZP space, but each of those each coset is represented by a bunch of these elements that represent my sets. So I haven't told you what my scheme actually is. I'm just telling you, I'm setting the stage, and I'm telling you that these are going to be two important values that I'm going to use. I'm going to hide them in some way. I haven't told you how, but I just wanted you to set the parameters here and tell you that these are two things which are going to be useful in this scheme. I haven't told you exactly what this is. So I with the small representation is not public. We don't actually want to give out I. There's no need to give out I. Our scheme is going to be such that we won't be able to hide I. So, but it would not be small elements within it. Okay. So it would you will have like larger. You could figure out elements within this ideal, but they would have these coefficients which would be large, not small. They would be of size comparable to Q. You could get but that would be large. Yeah, you could, but I mean, there's no point of giving it because we don't need to. Yeah, I mean, when you will generate the scheme, you will know the one generator file. Yeah, that happens. Yeah. So P is going to be at least exponential in the security parameter. For some applications, it might be okay to have something small, but for most applications, you will need it to be large. Yes, Z is also private. Okay. Okay. So now let's get to what the scheme things look like. Okay. So you have this space as we had these sets. And these are going to correspond to these cosets now, 1 plus I, 2 plus I, and I. And the addition and multiplication operations can be naturally defined here. And recall, I also had this large Z. So how am I going to define this set S1? Okay. So how I'm going to define is that I'm going to take an element in S02 and divide it by Z in RQ. Okay. So this is an element in R. But I'm going to sample a small element in this set. Okay, so I had a requirement that things are only going to work for something small. I didn't tell you how to sample or anything like that. But if I somehow got hold of a small element in this set, then the same element is also, it's the same element in RQ, because Q is very, very large. And then if I divide it by Z and do all the operations in RQ, then I'm going to represent this element as my S1. So Z is just random in RQ. There's no requirement on Z. Yes. So this is the representation that things are being done in RQ. So whenever I use the square brackets for the Q, I'm meaning that operations are being done in RQ, not in R. Yes. So if you look at a small element in here, it doesn't matter whether I look at an R or RQ, it's the same element. Right? Yes, yes, yes. It's not over. So you won't have those definitions if you will look in RQ. But I'm saying, look a small element here. Now, take it mod Q. It has the same representation because it's already small in R. And then divide it by Z. Yes. Q, yeah. Yes. Yeah. In RQ? So in RQ, with most of them are going to be invertible, right? Yeah. So if Q is large, with the high likelihood it's going to be invertible. If it's not, just reset. Yeah. Yes. Right.
But you didn't require that.
No, no. Right. Okay, so C is supposed to be a small multiple of? Yes, yes, yes. Z is not public, right? So yeah, yeah.
So I can just represent
Yes.
element by one to
Yeah. Right. Which is not necessarily small. It can be big, but it's not. It could be smaller than P. Not small. Yeah, yeah, yeah. That's trivial, yes. But you don't have a Z, right? I mean, Z is not public. If you have Z, yes, yes, yes. So right now I'm just telling you how things look like. I haven't told you how they're generated in the scheme or how. Yes. Yes. Yes, but with small coefficients. Yes. Well, I mean, not 2, but yes. Yeah, yeah, yeah. Mm-hmm. Yeah, if you selected C from I, then you would have a level 1 encoding of the 0, right? So, oh, this is this. Yeah, so this will be this value. You will then be in this set. So if you sample a small element in I, you're lying in this set, right? And then if you divide with Z, then you get an element here. No. Right. Yeah. Come again? Yes, it does. Yes. No. So Z inverse is not in R, right? So if you start doing operations in RQ, Z inverse is in RQ, not in R. So if you pick Z randomly, it's going to be with high likelihood not in R. Yes. Right. Yes, 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 yes. But Z inverse in RQ is so in R it doesn't even make sense to take its inverse, right? Right. Back, yes, yes, yes. But then it will only be if the C because you're taking mod Q along with. Yes. Okay. Okay. So again, addition now is in the represented forms is easy. So if I have an element from if C was in S plus I, and if I give you C by Z, and D was in T plus I, and if you had D by Z, and if you added them in RQ, you get C plus D by Z. Yeah. So that I haven't gotten to that yet. Okay. B is big, smaller than Q. Yes, yeah. Right. Yes. Right. It does well. I mean, well, yes, if you're moving to the same. So we'll get to there. So,
The question is, in my after two elements that are better.
yeah, you could add. If you're adding two things in RQ which are a different.
No, nothing.
Yeah. You could add them, but we don't know what will happen yet. Yeah. If you want to add things at the same level, so if C by Z and D by Z are both in level 1, if you add these encodings in RQ, then what you get is an encoding of the sum in the first level. Okay. And if C and D were short, then hopefully the sum is also not going to be too large and things are going to be okay. So this is just like the FHE requirement. Similarly for multiplication, if you multiply, then the exponents get multiplied, and so you go to the coset corresponding to the multiplication, and as long as things are short, both C and D are short, hopefully the multiplication will not be too large. But the difference arises from the fact that if you're multiplying two entries at the first level, then these Z's get multiplied and you have a Z squared there. So you're getting an encoding at the level 2. Well, I mean, it's going to become large, but the thing is we're going to have Q so large that this is all going to be much smaller. Yes. Right. So the thing is, you want to think of this as Z. So normally when you have the discrete log setting, you're exponentiating G1 with A. So you want thinking of it as being re-randomizing the thing. So this Z is kind of re-randomizing everything here, and we don't want you to learn what this C is. So if Z has some special properties, hopefully that might be able. Okay. Well, I mean, if Z is random, and yeah. Yeah. Okay, so in general, level K encoding of the coset S plus I looks like of the form C by Z to the K, where C is a short element in the coset S plus I. And an addition at level J can be done by just adding the encodings at the level J. And if the sum of the numerator still remains small, then you would be you will have a valid encoding, like an encoding with a small. So multiplication is analogous, just that the exponents of the Zi's get added up. So you now move to a higher level of encoding. Any arbitrary polynomial which is fixed a priori. Okay, so this is like a somewhat homomorphic encoding. You can go to a level that you want, and what I haven't told you is how to sample. That gets back to Wadin's question, and how to do this equality check. Okay? So you want to be able to do an equality check at the last level, which is the nth level, and you want to be able to sample at the 0th level. Like, so if you recall the property, the next, okay. So, well, I mean, you can always, if you want to check equality before, you can always go to the last level and check equality there. There will be a procedure to do that, but yeah. Okay. So how is sampling going to work? The idea is that G itself is small, so if you sample something from a wide enough region, which is defined by something wider than the smoothing parameter of the ideal I, then you will get something random. Okay, so maybe I'll say. So think of think of this box as defining as the lattice corresponding to this ideal I. Okay, and it tessellates the space, right? If I sample from a distribution which is much larger than one of these boxes, then I will sample something which comes from one of the cosets of I and is going to be kind of uniform in the sense which coset it comes from. Yeah. One. So this is something that Daniel has better. So the idea is that if you have this box represents the lattice corresponding to this ideal I, and am I saying it right? And if you look at large enough number of boxes and you pick a random point, you will hit a random coset of I. Yeah. But P is not as small as we want. It's not. It's still large. It's smaller than Q, but it's large. I mean, not good a bit big.
So why is it called smooth?
Originally it's really bumpy, I'm glad, but eventually it's
Okay, so the question was how do we, so far I just told you how we have how these encodings look like, and you could sample at level 0, but how are you going to encode values of your own?
So why is it zero?
No, I'm going, okay. So the question, if I understand correctly, is that we sample at level 0, why can't something like this work at level 1? Because, I mean, we have to do this division by Z in RQ, and the sampling is being done in R. Yes. Right. This is level 0 encoding of that coset. I don't know which coset it is. Yes. Okay. So the question is, thanks for, so the question is, how do you encode sample from S0P byte, right? So, so we're not going to be able to encode a specific value. We're going to be able to encode a random value. We won't know which value, which coset it is, but we'll be able to get something. Does that make sense? Well, I mean, you can then have a large value, not a small one. Are you saying just use P by 2? Yeah. But if you know G, you can do the lat. If you don't know,
The relation of the values showing the small.
yes, 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 right. Okay, right. But you cannot, yeah. So you get something which is random in one of them. Right. Yes. Randomly from one of them, and you get something small which is in one of them, of course, and it's small, and it's in which one it is from is random. Can sample. Yes, 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 yes. So the question is, or the statement is, that if someone knows G, then he can actually sample from the the coset of his choice, and that's. Right. So in most applications, yeah. So in most applications, you're not looking for sampling a fixed element. You're just trying to sample the random. So in fact, all the applications that I stated, in fact, in no application that we've come across has that been a problem. Okay. So how would you encode specific elements? To enable encoding of a specific element, I'm to give out an encoding of 1 at the first level. So sample A from the coset 1 plus I, such that A is small, and give out Y equal to A by Z, okay, in our queue. And if you want to, then if anybody wants to encode a random value, they can sample a C as I described before, in a mysterious way using invoking Daniela's new lecture, and then when we multiply this value C with Y, we get an encoding of this at the first level. So this is sampled from the coset 1 plus I. It's a short element in 1 plus I. Right. Okay. Yeah, this is level 1. If you multiply C with this level 1 encoding, you're going to get an level 1 encoding of C itself, right? Or the code. Yes, yes. Okay. We're going to make Y public. Okay. And if you want to just keep moving to the next level, you can just keep multiplying with Y, and you keep moving to the next level. Okay. So let me give so how does equality checking work? Note that it suffices to check at the last level that something encodes 0. If you can do that, then you can subtract the 2 encodings at the last level, check that it's an encoding of 0, and that's enough. Okay. By the way, that also answers your question as to how do we check equality at lower levels. You can always multiply with the encoding of 1, go to the highest level, and then check equality at the final level, right? Because the parameter, so yeah. So his question is, why can't we just do the equality check at a lower level directly? Why do we have to go? So I'm going to give the equality check procedure now, and from that it will be clear that it can only be done at the highest level. Okay. So we're going to enable zero testing, we're going to publish this extra parameter which looks like HZK by G. So recall that ZK always was in the denominator for the encodings, and now it's going to be in the numerator. And we're going to have G divided here, and so this, giving this thing by itself is bad. Then you're giving something which you can multiply with things and So we add this noise parameter next to it, and it's a random value of size, say, root q. It's a large enough value. Yes. Okay. So to test if u encodes a 0, what you're going to do is that you're going to multiply c by zk with this 0 test parameter, and you get ch by g. And there are some caveats here, but this should look small if c isn't the ideal. So we will, yeah, good question. So the question is, why dividing by g here? It just works because we're in RQ. I guess that's the question. Yeah. So the point is, we additionally have this requirement in our setting that we will sample g such that g inverse is not too large. Yeah. Well, in the field of fractions, in K, not in. Okay.
The thing is, if C is in I, then C is of the form of C prime times G.
Right.
Then when you divide, you divide out. Hopefully that C is of the form of C prime times
G. And
hopefully C prime.
okay. 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 So the question. So if you look at C, this looks like C prime G, right? And if I look at 1 by G in K, it's the field of fractions here. It's the cyclotomic field, not the. And then if you look at C by G, within K, if you do this operation, it's also going to be in R. Well, no, not necessarily.
That's what we really want.
Yes. Okay. Okay. So if you have you look at 1 by G in K, and you have C prime G by G within. You know that now you want to argue that this is. We know that this is in R. Now you want to argue that this is small. How you can argue that is that if C inverse G and G 1 by G, you know, all of them are individually not too large, then the product will not be too large. Okay.
Even only
Is it if and only if? So the question is, so if it is encoding of 0, then yes, it's going to be. If it's not an encoding of 0, then there could be some, if you couldn't have malicious encodings for which things could go bad. Okay, so there is one clear problem here which I'm going to tell. So let's say we didn't have any of this 0 test parameter, so no 0 test parameter was given out. At least the decisional Diffie-Hellman problem should be hard. Okay, so we're going to see that it actually is not hard, and there is something that needs to be done to make it hard. Okay, so what the decisional Diffie-Hellman problem is, so if I have these, think of these are level 0 encodings of S, T, ST, and R. So if I encode these things at level 1, like if I give you a level 1 encoding of S, a level 1 encoding of T, and a level 1 encoding of ST or R, you shouldn't be able to tell which one it is, okay, where R is random. Well, it is easy to sample a small element in the coset, so CS, without knowing S. Well, you can know S by doing the reduction then, and CT, as well as R. But how do I sample CST? Okay, well, just sample a random one and assign it. Okay, the question is that it's actually difficult to sample from S0S, but we can actually sample CS without knowing S, and then you can calculate what S is. Okay. But there in the DDH, the question is in the DDH problem, you're given G to the A, G to the B, but those A and B are sampled randomly, anyway. Right? Okay, one way to compute the CST is to just multiply CS and C. Wow. we can then encode these values. We can just multiply them with y. Recall that y was the level level 1 encoding of 1, and you have all these encodings. Or you could also generate the level 1 encoding of CR. Now, I mean, is it the last encoding indistinguishable from random? Well, clearly not. You can just multiply US and UT, and Y is public, and you can check. And the problem is that we are giving, this is a specific encoding corresponding to this coset. It's algebraically related to the other ones. We want to re-randomize it. Okay? So what's going on is that we're giving a specific value here, and we would like to re-randomize it within a space. Well, it's for enabling that, in our public parameters, we'll give out encodings of 0, level 1 encodings of 0, many of them. And if you add random linear combinations of these encodings, the thing's going to grow a bit larger, but hopefully it'll be random enough. Right? So you have a value, you want to re-randomize it, you just add a bunch of random encodings of 0. So the problem is that the question is why does this solve the problem? The problem is that this UST is inherently tied to the values here, because you just obtained it by multiplication. Right. Yes. So the answer is that the point is you want to multiply and add some noise, such that once you add that noise, it becomes random enough. Yes, yes, the noise divided by y. Yes. Right. Yes. So y does not have this property. The y is an encoding of 1, and if you add enough, well, I mean, you're adding zeros, right? So if you add, okay, we'll see in the next slide. There is a theoretical explanation for it. So if you add random linear combinations of it, you get re-randomized it, and you can keep doing it again and again. And actually, there's a statistical lemma by Agarwal, Gentry, Halevi, Sahai, and the idea is that it's doing this, adding these random zeros, is statistically the same as sampling a short element from this set. Right? So there couldn't be a better way of doing it.
So you are publicizing
yes.
from short element to I?
Not the element, we're not, so x0, x0 prime, x0 double prime are not elements of I itself. These are at level 1. So this is the complete picture. Our parameters consist of this level 1 encoding of 1, A being from the coset 1 plus I. Xi's, these are the level 1 encodings of 0, Bi's being from the ideal itself, and the 0 test parameter. If you want to encode something, you sample a value C according to the discrete Gaussian, and then you multiply it with the level 1 encoding of 1, and you add some noise to make it look random. Okay? And the 0 test can be applied. You can raise the value to the kth level, and then check for, multiply it with the equality test parameter, and if the value is small, then you know that this is encoded. So I'm getting to assumption. Yeah. So the question is, what is the assumption, right? Yeah. So the VK parameter, the 0 test parameter, is what's just introducing this new term. So the re-randomization, you could have a slightly stronger variant of n-true, which would allow you to maybe argue this. But the big departure is at VK. And actually, as we will see, for a number of applications, you actually don't need this 0. Yes, so I don't know if I should use the word slightly. It's stronger, but I think that maybe the VK part seems much more stronger than the in terms of.
Some into like
These are low, yeah. So the point is that it's not it's like n through because it's the values which you're giving away are encodings of 0, which are like the ciphertext. And okay, so there are a lot of variants that we could think of. One is instead of having the same z, you could have different zi's, and then this will start to mimic the asymmetric multilinear map. So you could give out a bunch of encodings of 1 in each of the zi's, the zeros corresponding to each zi that you give. Now the difference is going to be in the zero test parameter. You're going to have instead z to the k, but the product of all the zi's. Okay. You could have something which is partially symmetric and partially asymmetric. So you could have, instead of having zi, just the product, you could have some zi with some power. So I'm going to clearly state the assumption that we're making and the different variants of assumptions that can be made. So if you want to try to break them, then this is what you can focus your efforts on. So this is like the simplest variant where I'm not giving, I'm always going to give the zero test parameter, but I'm not giving encodings of 1 and 0. So what I'm giving you is an encoding of A0, A1 up to AK, K being the level of multilinearity, and I'm giving you the zero test parameter. Okay, this is what I'm giving you, and the challenge element is product of AI with ZK, and your goal is to distinguish this from something random. So even without the zero test and the encoding for 1, this assumption is already starting to be useful. Okay. You could consider the easier variants when you start giving away encodings of 0 and encoding of 1 at the first level. What about? They are just random. Yes. Yeah. So yeah. Yeah. Oh. So the question is, what is the precise distribution for A0 to AK? And the answer is that these are just sampled from the Gaussian corresponding to the smoothing parameter, like from a broad enough larger than the smoothing parameter of the lattice defined by ideal I, and so they'll come from one of these sets uniformly, each of them. And you can make this problem easy by giving away encodings of 0 and encoding of 1. Okay? And the other weakening that can be made is something where you're doing general computation. You're not just multiplying k things. So I can give you an example. So the question could be, if I give you an encoding of AB by Z square, something in BC by Z square is still ABC by Z cube. In the case of when k is 3, is this still indistinguishable from an encoding parameter? Okay. So this is the second weakening that you could think of. Yes. Yes. So this is, so the question is, why can't I just multiply these things, all these things together, and get something meaningful? Because when there are k plus 1 terms here, there's 0 to k. So if you multiply k of them together, then you don't get the product which contains all k plus 1 of them. That's the assumption. So this is.
Yeah. Absolutely.
Right. But then there's an h there, right? No, h is large. It was square root q size, right? Right. Then it would. Yeah. So even if there was something like that, h would still save you in some cases. But yeah. So the question is, why doesn't if you multiply a bunch of them together, what role does g play? And the answer is that the g is going to not cancel out because there's no 0 there. Okay. So you could make the assumption more difficult, and the idea is if instead of just having a symmetric setting, you use different z's for each one of them, and still it can be useful. And it seems that in fact we can do a lot of things with the strongest variant of this assumption, where you're giving this, but you're not giving this. But maybe in some cases you're also requiring a weakening in this. So there are a bunch of variants that you can think of that, and all of them seem good. Okay, so in terms of attacks, at least the scheme is not trivially broken. So straight line programs which do just addition, subtraction, multiplication of division will not be able to break the scheme. So this is similar in spirit to the generic group model, considered in the bilinear setting. And as was discussed before, without the 0 test parameter, it's more or less like the N2 problem. And so with respect to attacks, you could try to multiply these things. So if I give you an encoding of 1, encoding 0, and the 0 test parameter, you can try to multiply these things together and try to see what you get. So if you multiply a bunch of encodings of 1 with an encoding of 0 with the vk, then you're going to get something which is going to lie in the ideal defined by the principal ideal defined by h. And similarly, you could get terms which are defined by ideals for hg, and using them, then you can compute the ideal corresponding to g. But what you're going to get is not going to be something that's small, and this is going to be the basis for the hardness. So there's yeah, that's all I wanted to say. And to present this noisy cryptographic multilinear maps, the construction is similar to the N2 based homomorphic encryption, but with equality test parameter, and more cryptanalysis needs to be done. Yes. So it is needed for application. So the question is, why did we need the norm of the ideal to be a prime? So as I said, for some applications it may not be crucial, but for a large number of them you need it to be, because when you're doing the cryptography based on it, you're trying to do operations within that space. So if it is small, then things will start to break. So that it doesn't cancel with h, right? Otherwise, the if and only if. So the question is, why do we need this p to be large? So one reason is it's needed for the application. The other reason is that if it's too small, then your h, which is there in the 0 test parameter, could with some probability also lie in the ideal. In which case, the 0 test parameter will start to fail, right? Because h by g is going to be, h will itself have a factor of g which will cancel out. If h is in the ideal, then that's a problem. Okay. Yeah. Yes. Yes. So the question is, can we get averaging attack with these? Yes, but we. So so if you will multiply things like if you mentioned this. So if you multiply the terms here, then you're going to be able to get some multiples of g, right? And your goal is now to avoid averaging attack, where you get a bunch of multiples of g, and you want to figure out g from them, right? That's the. Okay, so it's the same thing with h and g. If you're able to figure out both of them, the scheme is broken. So the idea there is that when you sample from these ideals, you're not just multiplying with these values. You use a more sophisticated sampling procedure where you sample from the Gaussian defined by these lattices instead of just multiplying with things, which hopefully prevents people.
Averaging attack, right?
Yeah.
I mean, there is, we try to take some population, but really you could have parameters seem to not add up. These types of averaging that don't actually give you what you want. I don't know if you but at least to me, it wasn't a particularly convincing argument why you cannot possibly break it. It's just it didn't, the type of attack you were trying to find.
Yeah.
Well, we specify a complete procedure that we think is the safest thing to do.
Yeah. Yeah. Z is not small. Yeah. Was random in RT. Yes. No. Well, I mean, if you had this zero test parameter killed, right? So the question is, can we reduce it to like an n-true kind of an assumption? So the
Definitely, if you could break into a generalized
yes, yes. Right. Right. Yes. Yes, you need to. So you take significantly large size of the dimension. So it's going to, the dimension is going to grow not just with the security parameter, but also the level of multilinearity. So that when you add the multiplied things and the noise grows, then it starts growing even with the multilinearity. So the dimension is really large even with respect to multilinearity. So I don't remember exactly, but some polynomial in the security parameter and the level of multilinearity k. So level of multilinearity represents the number of terms that you would multiply. So if each of them adds some noise, the dimension now needs to grow with the level of multilinearity, so you can cope up with that kind of a scenario. Yeah.
Definitely, well, you know, let's put it this way. If K is a constant, then it should be that way. If you want K to be polynomial. So definitely, if you assume that the lattice problems are exponentially hard, assume that LLA is all that there is, then that. No, it's not in my English. Q being the square agenda is not. But it's, I mean, even making that count is something like.
So the best setting of parameter gives like a logarithmic advantage, right? So you can sample this G instead of size polynomial, but with super polynomial. So it might give some logarithmic advantage over LLL or something like that. But besides that, I don't think so. Yeah. Yeah, something like that. Yes. Right. Yeah. Yeah. So, right. Yes. So the part where you're saying it's a principal prime, that's heuristic. Besides that, you can argue things to be satisfied. But all these things being satisfied along with requiring, so you can get a polynomial probability arbitrary close to 1. So it's almost, you can get all the properties satisfied with the probability 1 minus an arbitrary polynomial. Except the property that it's a principal prime ideal. So for that, we do not know exact parameters on. We don't know. We don't have. At least I'm not aware of any density theorems which tell us what fraction of the principal ideals are prime. So we heuristically, and it's been used before. So we do know that the number of principal prime ideals with respect to overall ideals is going to be exponentially small because the class numbers for these is really large. But we do not know the fraction of principal prime ideals in which we kind of heuristically assume that among the space of prime ideals, if you can assume that it's a polynomial fraction, then you can sample things accordingly. Yeah. Yeah. Yes. So the question is that there is a fundamental difference with pairing and the WUL and this setting, in the sense that in the pairing WUL, once you specify the parameters, it's not nobody has a trapdoor or backdoor. Yes. So that's indeed a difference, and I didn't stress it enough. So maybe thought that nobody will ask that question, particularly in this audience. So the answer is no. We don't know how to construct that yet. But not in the non-interactive setting, right? Not interactive. So you need at least, I guess, 2 rounds of computation. Well, I mean, at least 4 rounds of computation if you want to do it completely. I guess with some weaker security, you could do better, but.